What if one ancient metal powers your modern world? Copper has shaped civilization for thousands of years. From the Bronze Age to electric cars, element 29 is everywhere.
You know, when you stop and look around at the sheer scale of the modern world, it is incredibly easy to assume that everything powering must be some kind of cutting-edge, lab-created synthetic miracle.
Oh, absolutely.
Yeah.
I mean, you look at things like electric vehicles or global server farms, aerospace engineering, and it all just feels highly futuristic.
Right. Feels like magic. But what if I told you that one of the most critical components holding our entire high-tech civilization together is something you could have, like, literally dug out of the dirt thousands of years ago?
It is a pretty wild contradiction when you step back and look at the timeline.
Yeah, because we're talking about a reddish-orange transition metal that has somehow remained incredibly important from the dawn of ancient civilizations all the way to the modern age of electricity.
We are relying on the exact same chemical structure to build out our electrified green energy grid that our ancient ancestors used to hammer out their very first metal tools.
Which is mind-blowing.
It really is. It's a material that just completely refuses to become obsolete.
Okay, let's unpack this. We are looking at a stack of sources on element 29, which is known on the periodic table by its chemical symbol Q.
Yeah.
And the mission for this deep dive is to basically understand its identity, its underlying physics, and why this specific material is essentially the nervous system of the modern world.
Well, to do that, we have to establish a core concept that drives this entire conversation.
Right.
I mean, copper is not just a metal.
No.
No, it is one of the foundational materials that has physically helped humanity move from ancient civilizations to an electrified technological world.
Yeah.
And its ability to do that, it actually comes down to a very specific atomic quirk.
Yeah, you mean the 4's orbital, right?
Exactly.
Okay, let's dive into that physical identity. Element 29. It sits right in the middle of the periodic table, and it's classified as a transition metal.
Yes, and that classification is key. So in its atomic structure, copper has 29 protons and 29 electrons. But the secret to its behavior, like why it does what it does, lies in its outermost electron shell.
Right, because the inner shells are full.
Exactly. Copper has a single solitary valence electron just sitting out there in its 4's orbital. And because it's just one electron, and it's sitting quite far from the positive pull of the nucleus, it's incredibly loosely bound.
So it's basically just barely hanging on.
Yeah, pretty much. When copper atoms bond together to form a solid, they arrange into this crystalline lattice. But those loose 4's electrons, they just sort of detach from their parent atoms.
And they form that, what do the sources call it? A sea of electrons.
Sea of electrons, exactly. It's a shared pool of electrons that just flows freely throughout the entire metal structure.
Which perfectly explains its malleability, because those atoms are sitting in this flexible, sort of fluid sea of electrons, rather than being locked into really rigid, brittle, covalent bonds, right?
The atoms can slide around.
Which meant that ancient humans, thousands of years ago, could just dig this reddish-orange stuff up and hit it with a rock. They didn't even need a high-tech forge at first.
No, they could shape it entirely cold.
Yeah.
And that malleability was a massive, just a massive paradigm shift.
Because before the Copper Age, we were just using stone.
Stone, bone, wood, yeah. Humanity was entirely constrained by the mechanical limits of those materials. I mean, if you hit a piece of flint too hard, what happens?
It just shatters into a million pieces.
Exactly. But when early humans discovered native copper, they found a material where the atomic layers could physically slide past one another without breaking the overall structure.
You could hammer it out.
You could hammer it, you could fold it, and force it to hold a sharp edge. It was revolutionary.
But I want to push back on that a bit, actually, because if I look at the historical timeline and the sources, pure copper didn't stay the dominant material forever.
No, it didn't.
It's like pure copper was a brilliant solo artist, but to truly change the world, it needed a bandmate. So why wasn't pure copper enough on its own? It seems like it had a performance ceiling pretty fast.
It did hit a ceiling, yeah. And it actually comes right back to those sliding atomic layers we were just talking about.
Oh, because it's too soft.
Precisely. Pure copper is very soft. If you were trying to chop down a massive hardwood tree or, clashed swords in ancient warfare, a pure copper blade is going to deform.
It's just going to bend and dull out immediately.
Incredibly fast. Under high stress, the planes of atoms in that crystal lattice just slide past each other a little too easily. So it really lacked the structural rigidity required for heavy industry or intense combat.
It's like taking a jar full of smooth glass marbles that just easily roll past one another. That's pure copper.
That's a great analogy, yeah.
But then humans discovered alloying. They found out that if they toss some jagged rocks into that jar of marbles, suddenly the marbles lock into place. They can't slide anymore.
That is an excellent way to visualize it. And those jagged rocks in this scenario were tin atoms.
Right.
Humans realized that if you melt down copper and mix in just a little bit of tin, you create bronze.
The Bronze Age.
Exactly. Tin atoms are physically a different size than copper atoms. So when they get embedded in that copper lattice, they distort it. They act like roadblocks, basically pinning those layers of atoms in place so they can no longer just slide past each other easily.
Wow. And the social and geopolitical implications of just pinning those atomic layers were staggering.
Oh, utterly transformative. If we connect this to the bigger picture, the creation of bronze fundamentally redrew the map of the world.
Because it was so much stronger.
Because it was significantly harder and more durable. It allowed for the mass clearing of forests for agriculture, carving heavy stone for monumental architecture, and fielding these devastatingly effective militaries.
Empires basically expanded just to find more tin.
Exactly. Trade routes spanning thousands of miles were established strictly to secure tin, and entire ancient civilizations rose and fell based on their access to this specific metallurgical chemistry.
So copper essentially builds the ancient world, ushers in the Bronze Age, and then it just kind of hangs out for a few millennia.
Yeah, it becomes kind of a background character for a while.
Right. It's used for roofing, for coins, for pots and pans. But then we leap forward to the 1800s. And I have to ask, how did an ancient metal become essential to electric cars and modern technology?
Well, it found its second revolutionary purpose, and this brings us right back to that loose 4s electron we started with.
Ah, the single valence electron.
Yeah. When humanity finally figured out how to harness electromagnetism, we desperately needed a medium to transport it.
We needed wires.
Right. We needed a material where electrons could be pushed from one end to the other with minimal resistance.
And copper's sea of electrons was just sitting there waiting. It's like the electrons moving through copper are like cars effortlessly cruising down a wide open, perfectly paved highway. It's just the ideal path for power.
It really is. And that single property is what makes copper absolutely essential to modern electrical infrastructure. It is the literal lifeblood of wiring, electric motors, generators, transformers.
Basically everything.
Everything. Electronic systems that power homes, factories, transportation networks, and communication equipment. All of it relies on copper.
But why is copper so good at carrying electricity compared to other materials? Because, I mean, wait, isn't silver actually a better electrical conductor?
It is, yeah. Silver has slightly lower electrical resistance.
So why didn't we just build the grid out of silver? Or on the flip side, why not use something incredibly cheap and lightweight like aluminum for everything? I mean, it feels like copper just got lucky by being the middle child.
I wouldn't say it's just luck. It's more of a very specific intersection of physics and economics.
Yeah.
You're right about silver, but silver is geologically rare.
Oh, right.
Trying to wire the entire planet, every motor, every transformer with silver, it would bankrupt the global economy almost immediately.
Okay, fair enough. What about aluminum then?
Now, aluminum is an interesting counterpoint. It is cheap, it's abundant, it's lightweight, and we actually do use it for high voltage overhead transmission lines.
Oh, we do, but we don't use it in our homes or in our smartphones and sensitive electronics. Why not?
Because of thermal expansion and oxidation. Aluminum expands and contracts with heat much more drastically than copper does.
Oh, so it moves around too much.
Right. If you wire a house with aluminum, over time, the heating and cooling of the wires as power flows through them causes the connections at the outlets to physically loosen.
Yikes. That sounds dangerous.
Very. That loose connection causes electrical arcing, which causes house fires. Plus, aluminum forms this insulating oxide layer on its surface, which adds resistance.
So copper just hits the sweet spot.
Exactly. Copper sits in the absolute perfect sweet spot. It is a phenomenal conductor, it is dimensionally stable, it resists catastrophic oxidation, and it's abundant enough to pull out of the earth at a massive scale.
So it became the superhighway for the electric age. When a power plant generates a voltage, it's essentially applying pressure, right?
Yes, electromotive force.
And because copper has those completely unbound valence electrons in that transition metal structure, that pressure just cascades down the wire near the speed of light, atom to atom, with almost no traffic jams.
Precisely. And because there is so little resistance, Very little of that electrical energy is lost to the environment as heat.
It's just highly efficient.
That efficiency is why we use it for everything.
But wait, copper isn't just about electricity, right? We've talked about how easily electrons travel through this lattice, but those same mobile electrons also carry kinetic energy.
They do, yes.
So if you excite them with heat, they race through the metal just as fast as an electrical current. It's a master of heat, too.
Yeah, that is the mechanism behind its thermal conductivity.
Yeah.
The two properties, electrical and thermal conductivity, are inextricably linked here.
Okay, so how does that work in practice?
Well, when you expose one side of a piece of copper to a heat source, you are increasing the vibrational energy of the atoms, but you are also giving kinetic energy to those free-floating electrons.
And since they can move so freely...
Exactly. Because the electrons can move so quickly through the lattice, they transfer that heat to the colder regions of the metal incredibly fast.
Which is why it's crucial for cooling systems. I mean, whenever engineers need to move heat away from a sensitive component like a high-performance computer chip, or pull heat out of an environment rapidly in an industrial heat exchanger...
Or even just an everyday HVAC system.
Right. Copper is the immediate go-to material. It just pulls the heat away before the system can melt itself down.
That's highly effective.
Okay, here's where it gets really interesting. We've talked about what copper does invisibly, shuttling electrons and kinetic energy around. But its visual transformation is fascinating.
The patina.
Yes. When exposed to air and moisture, its surface gradually develops a greenish layer. It doesn't stay that shiny reddish orange.
No, it goes through quite a chemical reaction. And obviously, the most famous example of this in the world is the Statue of Liberty.
Right. When the Statue of Liberty was unveiled in New York Harbor back in the 1880s, it was actually this gleaming, reflective copper shell. It looked like a giant penny.
It did. But over a few decades, you have the salty air and the moisture in the harbor, and that facilitated a series of chemical reactions, gradually transforming it into that iconic matte green color we know today.
But the mechanism here is what I don't quite get. Why doesn't it just rust away to nothing, like iron does? I mean, if you leave a steel car out in the salt air, it eventually disintegrates into dust.
It's a completely different chemical process governed by a concept called the Pilling-Bedworth ratio.
The Pilling-Bedworth ratio.
Yeah, it basically dictates how the volume of an oxide layer compares to the volume of the base metal itself.
Okay, so it's about physical space.
Right. When iron reacts with oxygen and water, it forms iron oxide rust. But the rust molecules physically take up significantly more space than the original iron atoms did.
Oh, so it expands.
It swells up. And as it swells, it creates internal mechanical stress. Eventually, it cracks and flakes off.
Which just exposes more fresh iron underneath.
Exactly. This constantly exposes fresh iron to the air, and the process just repeats over and over until the metal is entirely eaten away.
So iron basically destroys its own protective layer.
Yes. But copper behaves entirely differently. When copper reacts with oxygen, sulfur, and carbon dioxide in the atmosphere, it forms copper carbonates and copper sulfates.
And those are green.
Yes, that's the green patina. But crucially, the molecular volume of these new green compounds is incredibly compatible with the underlying copper lattice.
Oh, so they fit perfectly.
They do. Instead of expanding and flaking off, the patina tightly binds to the surface. It forms this incredibly dense, impenetrable, passivating shield that seals off the pure copper underneath from any further atmospheric attack.
Wow. So the metal essentially scabs over to protect itself.
That's a great way to put it, yeah.
It's almost biological, which actually serves as a perfect pivot because copper isn't just reacting with the external environment. It is quite literally inside of you listening right now.
It is, yeah.
We require small amounts of copper to survive.
It is a critical micronutrient. And interestingly enough, the reason our bodies use copper is the exact same reason the electrical grid uses it.
Its ability to handle electrons.
Exactly.
But how does that work in biology? I mean, we obviously don't have little copper wires running through our veins.
No, we don't. But we do have enzymes that need to shuttle electrons around to facilitate chemical reactions. And one of the most important ones is called cytochrome C oxidase.
Cytochrome C oxidase.
Yes, it sits inside our mitochondria. This enzyme is responsible for the final step of the electron transport chain, which is basically how our cells generate ATP.
And ATP is the actual energy currency of the body, right?
Right.
So copper is generating power at a cellular level.
Precisely. At the core of that enzyme are copper atoms. Copper has this unique ability to easily switch back and forth between two oxidation states, so C1+ and Cu2+.
Meaning it can grab an electron and let it go.
Exactly. It can accept an electron, hold it, and pass it off to an oxygen molecule without destabilizing itself. Without copper facilitating that microscopic electrical transfer, cellular respiration literally grinds to a halt.
This raises an important question regarding biological safety, though, because if copper is that highly reactive and that good at moving electrons around, having loose copper just floating around the body sounds really dangerous.
Oh, it is. It's a very delicate biological tightrope. Balance matters immensely. We've evolved highly specialized transport proteins whose sole job is to safely carry copper atoms through the bloodstream and deliver them into the cells.
So they keep them locked up?
They keep them tightly bound so they don't cause random oxidative damage. If you have a copper deficiency, obviously your mitochondrial energy production drops, leading to anemia, neurological issues, bone weakness.
But if you consume too much, or if those transport proteins fail,
Then the free copper accumulates, particularly in the liver and the brain. And because it is so eager to transfer electrons, it starts generating free radicals that just tear apart cellular membranes and DNA.
oh wow.
Yeah, heavy metal toxicity from excessive copper exposure is catastrophic to human tissue. The body demands absolute balance.
That's wild. So we have this metal that drives cellular energy, protects itself from the atmosphere, and powers the electrical grid. And we really need to look at its role in modern technology from a life cycle perspective, too, because the sources point out something regarding recycling that frankly puts things like modern plastics to shame.
Ooh, the recycling profile of copper is unparalleled. It really is a superpower. We hear a lot about recycling paper or plastic, but the reality is that those materials degrade.
Right, they get word every time you melt them down.
Exactly. Plastics are made of long, complex chains of carbon molecules, polymers.
Yeah.
Every time you heat them up to melt them down, you physically snap some of those covalent bonds. The chains get shorter,
And the plastic gets weaker.
it gets weaker, it gets more brittle, until eventually it just can't be recycled anymore and it ends up in a landfill.
But copper doesn't have carbon chains to snap.
No, it doesn't. Copper is held together by metallic bonds, that sea of electrons we talked about at the beginning. When you throw copper wire into a furnace and melt it down, you aren't breaking fragile molecular chains.
You're just getting the atoms loose again.
You're just adding enough kinetic energy to temporarily vibrate the atoms out of their crystalline lattice. The moment you let it cool down, they snap right back into the exact same perfect, pristine 4s orbital lattice structure.
Which means it can be recycled repeatedly without losing its fundamental chemical properties.
Absolutely zero degradation. A copper atom is a copper atom.
It's such a mind-bending reality to think that the copper inside the smartphone in your pocket right now could, theoretically, have been melted down from a medieval church bell, which was melted down from an ancient Roman plumbing pipe, which was originally smelted from raw ore during the Bronze Age.
It is entirely possible. The atomic conductivity and the durability remain completely untouched by the recycling process.
And why does that copper recycling matter so much right now?
Because mining low-grade copper ore from the earth is highly resource-intensive and environmentally taxing. Being able to strip down old electrical equipment, melt it down, and deploy it into new technology without losing even a fraction of a percent of performance is a massive industrial advantage.
Especially since we are going to need every single ounce of recycled copper we can get our hands on. We are currently undergoing the largest infrastructure shift since the Industrial Revolution.
The electrification boom.
Right. As technology develops, the global push away from fossil fuels and toward renewable energy is fundamentally a push toward element 29.
It absolutely is. Just think about the mechanics of an electric vehicle. A traditional internal combustion engine relies on, small explosions of gasoline to push mechanical pistons.
But an EV doesn't do that.
No, an EV relies on massive electromagnetic fields to spin a rotor. And to generate those fields, you need dense, tightly wound coils of copper wire inside the electric motors.
I read that an EV requires up to 4 times as much copper as a standard gas-powered car.
Easily. And that bottleneck isn't just in the vehicles themselves. It's the charging network, too. Delivering high-voltage DC fast charging requires incredibly thick, thermally efficient copper cabling just to handle the current without melting.
Because of the thermal conductivity we talked about?
Exactly. And then you step back and look at the macro level, the power generation itself.
Like wind turbines and solar farms.
Right. A single offshore wind turbine contains tons of copper just in the generator alone, plus the subsea cables required to drag that electricity back to the mainland. We are transitioning to this decentralized grid where power is generated in remote areas by the wind and the sun, And it all has to be transported via high-voltage lines to urban centers.
Not to mention the data centers required for modern computing and artificial intelligence.
Oh, the copper demand for data centers is massive.
So what does this all mean?
It means we are facing a staggering mathematical problem. The data centers, the global shift to EVs, the complete overhaul of the power grids, they all mandate an exponential increase in the demand for element 29. We simply cannot build the high-tech carbon-neutral future we are aiming for without unprecedented volumes of this highly efficient conductor.
It makes it strategically vital for future technologies. And it's almost poetic when you step back and view the entire timeline, connecting past, present, and future. This relatively unassuming reddish-orange metal acts as a continuous thread running straight through human history.
It really has been the silent partner of our evolution.
You have ancient humans pulling native copper from the earth, realizing it was malleable and using it to escape the limitations of the Stone Age. Then, civilizations engineer its atomic structure with tin to create bronze, giving rise to empires. Thousands of years later, modern engineers realize those same loose valence electrons make it the perfect superhighway for transporting electricity, using it to light up the globe.
And now, the engineers of tomorrow are relying on it to stave off climate change and build the next generation of infrastructure.
It's an incredible story. If you enjoyed this journey through Element 29, subscribe to Atomic 118. We're exploring all 118 elements and the incredible stories hidden inside the periodic table.
From ancient tools to electric vehicles, copper has been quietly helping civilization move forward for thousands of years. And element 29 may be just as important to the future as it was to the past.